Every giant was once a baby, though you may never have seen them at that stage of their development. NASA's most advanced space telescope, the James Webb Space Telescope, JWST, is shedding light on the formative years in the history of the universe that were previously beyond our reach. This remarkable instrument has opened new avenues for understanding cosmic evolution, and its discoveries are reshaping our comprehension of the universe. In June 2022, the JWST made groundbreaking revelations, unveiling a plethora of faraway galaxies when it first captured its deep field image. This milestone was not just a routine observation. It was a monumental moment in astronomical history. Suddenly, galaxies began to emerge from the darkness of time and space, making their presence known in ways we never imagined possible. The universe, for the first time, began to seem far stranger than we ever thought it could be. Galaxies began to materialize from what scientists believe to be the universe's dark ages, raising profound questions about the established scientific models that describe our cosmos. These findings not only challenge existing theories but also ignite a renewed interest in the evolution of the universe itself, creating excitement among both professional astronomers and amateur stargazers alike. The ability of the JWST to peer deeper into space and time has revealed a cosmic landscape filled with unexpected phenomena. It wasn't just a couple of galaxies that the JWST found. It identified hundreds of them, leading astronomers to reevaluate their understanding of cosmic history. One of these significant discoveries came from an Austin astronomer named Stephen Felstein, who found a galaxy he named Maisie's Galaxy, an ode to his daughter, as they spotted it on her birthday. This personal touch adds a human element to the scientific journey, reminding us that these discoveries are not merely numbers and data points, but have real-world connections and stories behind them. Initially, Felstein and his team believed that the galaxy had formed almost immediately after the Big Bang, roughly estimating its age to be around 290 million years post-Big Bang. However, upon further analysis with more advanced equipment, they discovered that this galaxy is about 100 million years older than initially thought, cementing its status as the oldest galaxy ever observed, having formed only 390 million years after the Big Bang. This groundbreaking discovery raises the question: how many more galaxies like Maisie's Galaxy exist? The record holder for the oldest galaxy observed might not enjoy the top spot for too long. Currently, about 10 more galaxies are under evaluation by the JWST team, which could potentially be even older than Maisie's Galaxy. Fabio Picucci of the Harvard-Smithsonian Center for Astrophysics remarked, "We're seeing a rise of massive galaxies faster than we previously thought. The ages of some of these early galaxies are estimated to be just tens of millions of years, suggesting that our understanding of galaxy formation may need a serious overhaul." These findings could have significant implications for large structures of dark matter known as halos, which, according to our cosmological models, are thought to have sculpted early galaxies. The discovery of massive galaxies emerging so soon after the Big Bang presents a challenge to the existing understanding of how galaxies form and evolve over cosmic time. This has prompted scientists to ask critical questions. Were galaxies forming more rapidly than we thought? Were our models of cosmic evolution incomplete? Moreover, the JWST revelations are not without their complications. Some problematic and potentially model-busting early universe candidate galaxies still remain. The first among them is a class of galaxies identified by a team of scientists at the Swinburne University of Technology in Australia. The team found galaxies with billions of solar masses, comparable in weight to our Milky Way, from just an estimated 750 million years after the Big Bang. These galaxies are reported to be 10 to 100 times larger than galaxies previously observed in this era and are compressed into structures that are 30 times smaller than the Milky Way. What's more intriguing is that these galaxies appear to be hosting many more stars than astronomers thought would be possible. The fundamental understanding of how massive structures build up over time has been called into question, challenging the cosmological standard model. This raises important questions about the processes that govern star formation and galaxy evolution in the early universe. Are there unknown mechanisms at play that allowed these massive galaxies to form so quickly? Michio Kaku, a prominent theoretical physicist, has commented extensively on these revelations. He noted, "The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe. His insights underline the transformative nature of the JWST findings, suggesting that they may redefine what we know about cosmic evolution. Kaku emphasizes that such revolutionary discoveries prompt us to rethink our most fundamental assumptions about the cosmos. He further elaborated on the implications of these discoveries, stating, "We always thought that galaxies took billions of years to form. Now we're finding galaxies that are massive and well-formed just a few 100 million years after the Big Bang. This changes everything we thought we knew about the universe." He emphasized the need for a paradigm shift in cosmology, suggesting that the standard model may not adequately account for the complexity and rapidity of galaxy formation as revealed by the JWST. As we look at the broader picture, it becomes clear that the JWST is not merely a telescope, but a revolutionary tool that has the potential to rewrite cosmic history. The discoveries made thus far have implications that extend beyond individual galaxies, challenging the very framework of cosmological theory. This brings us to the question of galaxy formation timelines. Traditionally, scientists believed that it took billions of years to create a galaxy like the Milky Way, which houses around 100 billion stars, many of which are billions of years old. However, the JWST has identified 6 galaxies that existed just 500 million years after the Big Bang, some of which are up to 10 times larger than the Milky Way. Such findings contradict previous assumptions that there should not be primordial galaxies larger than the Milky Way that are only 500 million years old. Kaku expressed his concerns regarding these findings, suggesting, "Something is wrong. We may have to revise our theory of the creation of the universe." The implications of these discoveries are far-reaching, forcing scientists to revisit foundational concepts in cosmology and explore alternative theories regarding the evolution of galaxies. Not only did the JWST uncover more distant galaxies, but it also detected Milky Way-like galaxies at the edge of the universe that, according to our current physics, should not exist. Many of these early galaxies were rich with glowing gas, so bright that the gas itself could outshine the stars forming within. This newfound understanding reveals just how common such shimmering, infant gassy galaxies were when the 13.8 billion-year-old universe was around only 2 billion years old. Observations now indicate that almost 90% of the galaxies exhibited so-called extreme emission features, meaning they contained a significant amount of glowing gas. While studying these early galaxies, astronomers stumbled upon the most distant example of a galaxy that resembles our own Milky Way. The newly discovered spiral galaxy, named Sears 2112, appears to have featured a bar of stars and gas cutting across its heart when the universe was just 2 billion years old. This raises an intriguing question. How is it possible for a galaxy like the Milky Way to exist so early in the universe's history? Our galaxy, the Milky Way, is also a spiral galaxy featuring a similar bar structure. Scientists suspect that the Milky Way's bar rotates cylindrically, funneling gas into the galaxy's center and sparking bursts of star formation. Previously, astronomers believed this galactic structure marked the end of a galaxy's formative years, suggesting it should only be seen in older galaxies that have reached full maturity, perhaps those that existed halfway through the universe's evolution. Historically, with the Hubble Space Telescope's observations, scientists thought the early universe hosted very few barred galaxies. However, the discoveries made by the JWST are reshaping our understanding. The data collected indicates that barred spiral galaxies may not be a recent development in cosmic history. The discovery of Sears 2112 reveals that galaxies resembling our own existed almost 12 billion years ago, when the universe was just 15% of its current age. The implications of this finding are profound. Sears 2112 is observed at a redshift of 3, indicating that the light from this galaxy took almost 12 billion years to reach the JWST. This is surprising because galactic bars are believed to have formed about 4 billion years into the universe's life. The standard model of cosmology predicts that the early universe's physical conditions would have prevented the formation of such barred galaxies. Yet here we are, faced with evidence that contradicts long-held beliefs. Moreover, theoretical predictions from cosmological simulations struggle to reproduce such systems at these early epochs, leading scientists to ponder what is going on. We now need to understand which key physical ingredients are missing in our models. As one of the scientists associated with the discovery remarked, "If something is missing, we need to find it." This quest for understanding the early universe is reminiscent of the scientific inquiries that have shaped human thought throughout history, from Galileo's first observations of the stars to the groundbreaking work of Hubble. Each leap in our understanding has been met with both excitement and skepticism. The JWST stands on the shoulders of these giants, pushing the boundaries of what we know. And if you think this is the end of the surprises, consider this. Scientists believe that 85% of all matter in the universe is dark matter, a mysterious substance that eludes direct observation because it does not interact with light. Dark matter is thought to have played a crucial role in galaxy evolution and star formation as early as 380,000 years after the Big Bang. However, findings from the JWST suggest that, at least in the case of Sears 2112, galaxy evolution was dominated by ordinary matter, not dark matter, when the universe was about 2 billion years old. This is a significant discovery, as it confirms that the evolution of this galaxy was primarily shaped by baryons, the ordinary matter that makes up you, me, and everything we see, rather than the elusive dark matter. This new perspective adds yet another layer of complexity to our understanding of cosmic evolution and the roles different forms of matter play. As we navigate this exciting frontier of cosmology, it is evident that the James Webb Space Telescope has ushered in a new era of discovery. These findings are not merely academic. They are transformative, challenging the very foundation of our understanding of the universe. The secrets of the cosmos, once shrouded in darkness, are now within our reach, revealing a landscape that is richer, more complex, and more vibrant than we ever imagined. In conclusion, the James Webb Space Telescope is not merely a technological marvel. It is a beacon illuminating the darkest corners of the universe, urging us to rethink what we know and consider the vast possibilities that lie ahead. Every new discovery compels us to examine our understanding of the cosmos, and as we stand on the precipice of new knowledge, we invite everyone to join the conversation. What do you think about these findings? What implications do they hold for the future of cosmology? The discoveries made by the James Webb Space Telescope, JWST, have far-reaching implications that continue to evolve. As astronomers examine these groundbreaking findings, it's becoming increasingly apparent that our view of the cosmos is rapidly shifting. While the telescope's deep-field images have unveiled ancient galaxies, some of these structures appear far more evolved than expected for their age. The unexpected presence of mature, massive galaxies only a few hundred million years after the Big Bang has prompted many to reconsider our understanding of how galaxies form and grow. One of the key challenges to current models is the question of how galaxies can be so massive and well-formed so quickly. Previous theories suggested that it would take billions of years for galaxies to accumulate enough matter and energy to develop into the large, complex systems we observe today. However, the JWST has provided evidence that some of these galaxies formed much earlier, indicating a more rapid pace of evolution than previously thought. This raises the possibility that new, unknown processes may have facilitated the faster formation of these early galaxies, possibly altering our understanding of galaxy dynamics in the first few hundred million years of the universe's existence. A particular area of interest is the formation of supermassive black holes in the early universe. The JWST has detected signs of these monstrous objects at much earlier times than theorized. Some of the early galaxies observed by the JWST appear to host large central black holes, which would have required vast amounts of matter to accrete over a relatively short period. The existence of these early black holes challenges the traditional view that such objects could only form once galaxies had matured, as black hole formation typically follows galaxy evolution. Researchers are now forced to question whether these black holes played a role in accelerating the development of galaxies themselves, or whether their rapid growth was a result of entirely new processes still poorly understood. The discovery of ancient, well-structured galaxies so early in the universe's timeline also calls into question our understanding of the intergalactic medium and the conditions necessary for galaxy formation. For decades, astronomers have believed that the universe's cosmic dawn was a chaotic, murky time, dominated by scattered hydrogen gas and radiation. However, some of the galaxies observed by the JWST seem to defy this view, appearing to be well-structured and full of gas rich enough to support vigorous star formation. This could mean that the early universe had a more conducive environment for galaxy formation than previously thought, perhaps due to a more uniform distribution of matter or new types of galactic interactions that remain unknown. One other surprising discovery is the presence of a surprising variety of galaxy types at such an early stage. While earlier telescopic observations, such as those by the Hubble Space Telescope, suggested that early galaxies were primarily irregular in shape, the JWST has uncovered galaxies with a variety of shapes, including spiral and elliptical galaxies, which were thought to form much later in the universe's history. The detection of barred spiral galaxies, such as Sears 2112, has particularly shaken long-held theories. These galaxies, which are remarkably similar to our own Milky Way, challenge the view that spiral galaxies could only form after billions of years of galactic evolution. This new data has led scientists to propose that spiral structures could have developed much earlier than previously thought, or perhaps they are a natural phase in the evolution of galaxies that occurs under specific conditions. The JWST's observations of gas-rich galaxies are also shifting our understanding of star formation. In many of the earliest galaxies observed, star formation appears to be far more active than expected. These early galaxies seem to be forming stars at a much higher rate than what current models predict for their age. This rapid star formation could have been driven by a number of factors, including stronger gravitational interactions, more abundant gas reservoirs, or even the influence of dark matter in ways that have yet to be fully understood. These findings suggest that early galaxies were far more active than previously imagined, which could have led to more rapid growth and transformation.